So hi, this is a polar coordinates question. It's taken from the Pearson's Edexcel textbook for FP2. I suspect it's a past paper Edexcel question from a few years back. Looking at it, there's a few things I would say before I start. The range is a little bit unusual. Normally we define them between minus pi and pi rather than 0 and 2 pi. It's not going to change the shape at all. It just means that we're going to have a different polar coordinate for point C. It would normally be a negative, but here it will be at some number above pi. Also, the shape of these curves, it should be something familiar. We really should be familiar with curves of the shape R is equal to A plus B cos theta, or indeed R equals to A plus B sine theta. We really should be familiar with those types of curves. Limaçon shape, apparently. The special case is where these two numbers are the same, where you get the cardioid. Just talking about it briefly, this shape here has got this little dimple in it, which refers to this curve here. And the reason it's got a dimple in it is because this value is 3, which is more than this value, but less than double it. And in those cases, what you have is the shape going the other side of our R there, of our initial line. So it will have a value of minus pi, or pi will have a value that side. And yeah, I mean, but it'll have a dimple in it because it'll start curving back on itself because of the relative values of these two. Were it to be 4 plus 2 cos theta, it would hit the line flat. Okay, not necessarily exactly where I put it there, but it would hit it flat. And once it starts becoming greater than, it will hit it at more of an angle like that. It'll look more like an egg type shape. And talking about egg shapes, this one is an egg type shape because ignoring the minus, all the minus does is it changes the relative position of this. If it were plus 2 sine theta, it would kind of come this side. So, but looking at the relative values of these two, 5 and 2, we have this time the one is more than double the other, in which case we've got this egg shape and there's no dimple. And then we have the case where they're equal to, and that's when you get this cardioid shape when A and B are equal, which isn't the shape here. And when actually this number is greater than this number, we have it coming in at the initial line but at an angle similar like that. Okay, so it's all in the textbook, and maybe I'll do a separate video on that at some point on those particular curves, because this family of curves is something we should really know. And indeed, if we talk about sine theta, the symmetry then actually comes around this way. In other words, it's around the vertical line, the line theta equals pi by 2, rather than around the line, the initial line. So a lot of time we have cos theta, but sine theta would just would kind of basically rotate it by 90 degrees. Okay, but anyway, I haven't even really started the question yet. I thought to just kind of use that as an opportunity to talk about the shape of these curves, because I know some of you not really happy with having to sketch these curves sometimes and whatever. Okay, right, so let's look. Part A is going to be incredibly straightforward. And whenever it says write down, they literally think that you can write it down. Well, A relates to the points on this curve here where theta equals 0. Okay, so theta is equal to 0 at A, and at B theta is also equal to 0. So putting 0 into here, we get 1. So we get, for point A, we have 5A. And putting 0 into here, we get 2, so that's 5 minus 2, which is 3, so we get 3A 0. Okay, so that's that part done. Okay, let's move on to the next part. Okay, part B It says find the polar coordinates at point D and C. Okay, I see a certain amount of symmetry going on here, but again, be careful because we've got the range between pi and between 2 pi and 0. But we're equating these two. Okay, because R is obviously going to be the same where they meet. So we have A 3 plus 2 cos theta is equal to A 5 minus 2 cos theta. Okay, so looking at this, we can cross off the A here. Obviously they cancel. That's going to give us 4 cos theta equals 2. Cos theta equals to half. That would normally give us theta is equal to pi by 3 and minus pi by 3. But note, we're not looking at the negative values here because of our range. So let's add 2 pi to that and we get 5 pi by 3. Okay, so that's the polar coordinates. Note, we've got cos theta equals to a half. So if we put a half back into here or here, that's going to give us our 2 coordinates. So D it's going to give us 4a, isn't it? Because it's going to add 3 to 1 to there and take 3 add 1, which is 4, and 5 take away 1, which is also 4, which shouldn't be a surprise because we would expect the same value of a here. So that's 4a pi by 3 is D, and C is 4a minus, oh, not minus, 5 pi by 3. Okay, so that's the intro stuff done. Not too difficult at this stage, but then the difficulty is going to come with part C. Right, before we look at part C, the difficulty is going to be finding the integrals, the correct, which function to integrate and between which limits. It's surprising how easy it is to swap get the wrong curve for each bit. So let's get I'm going to actually annotate this, and this is R is equal to a 3 plus 2 cos theta. Right, now we want this area here. Well, the first thing I'm noticing is symmetry. So really, I'm just going to deal with the above of the line. I'm going to find this area effectively, or use the principle that area. If I double it, I'm going to get the whole area. Okay, it's clear that the symmetry could be adopted here. Just means we're going to have a few zeros in our limits. Right now, what we really need to do here is split it. We've got to think of this as 2 areas. We've got this area here, because notice the value of theta here between each of these. We've got almost lots of, when theta is between naught and pi by 3, because remember the polar coordinate of D is 4a pi by 3. So this is the line pi by 3 here. And to find this area, we're looking at this curve, and the limits are going from 0 around to pi by 3. And if we draw lots of these, they're going further out to pi by 3 here. So that's that area here. Okay, so let's just annotate that. Let's say that, let's call it area A1 if you like. A1 is equal to a half. Now the limits, as we say, because this is the line theta equals to naught here, the initial line. So we're going between the limits pi by 3 and naught of r squared, which remember for this one we're now dealing with this curve. Actually, I might have already made a mistake in what I've just said, but ignore it if I did, I can't remember. This is this curve here. That's this curve. So that's a squared 5 minus 2 cos theta squared d theta. Okay, right, now let's just do this in a different colour so we don't get lost. Right, now coming from here, we are, call this area A2. Now the limits are going, if you pick particular values, it's going all the way from pi by 3, but notice we're going all the way to pi here. So for example, extreme case here, this particular point is where cos theta equals pi, so that's actually got coordinate a pi, that particular one here. So we've got all values of theta between pi by 3 and pi in this curve. So let's rub all that out. Hopefully that's now clear. So that's our A2. Okay, let's swap back to blue. Okay, so A2 is equal to, and don't forget we're now on this curve here, because that's part there is that curve. So that's A2 is equal to half pi to pi by 3, which a squared brackets 3 plus 2 cos theta d theta squared. Apologies for the dogs barking outside. Okay, so in many ways that's the most troublesome part of getting these questions right, is getting the correct integrals with the correct limits. And then the rest is just taking care, because it's quite mechanical, and using what we know about integration. Commonly these questions obviously involve the integration of cos squared theta. So we'll just get on with it, but that is the real problem with is getting these limits right and get the integration right, where we split it into the two different bits. And it does take a little bit getting used to. One thing I will say, I have mentioned symmetry. So our required area, let's call it A, is going to be equal to 2 times A1 plus A2. So that's basically going to get plus 2A2, of course. That's going to get rid of the half of each of our areas. So let's work out the A1 bit first, the doublet, which is equal to pi by 3 to 0 a squared 5 minus 2 cos theta squared d theta. Now at this level we shouldn't be making hard work. I'm surprised what I see sometimes, people doing grids and smiley faces and second year further maths. Anyway, we shouldn't be struggling to to square this. So it's 25. 5 times 2 is 10, double that, so that's minus 20 cos theta. And 2 cos theta squared is plus 4 cos squared theta d theta. Now notice, I'm just looking ahead a bit, I'm going to get a 4 cos squared theta with the next one. So what I might do here, in a different colour, just to actually add to it, is to find the integral of 4 cos squared theta, because that will help us with both the integrals A1 and A2. Well, note that 2 cos squared theta minus 1 is equal to cos 2 theta. So that gives us that 4 cos squared theta is equal to 2 cos 2 theta plus 2. So that means that the integral of 4 cos squared theta is equal d theta is equal to the integral of 2 cos 2 theta plus 2 d theta. and that's going to be equal to sine 2 theta plus 2 theta plus c, but obviously we're not going to be bothering with that when we put it into our integral with limits in. So let's just have that in mind for our integrations to follow. Okay, so we have that equals to, let's change colour back to blue. That equals to a squared, and then that's square bracket 25 theta minus 20 sine theta, and as I say, we've already integrated 4 cos squared theta here, so that's plus sine 2 theta plus 2 theta from pi by 3 to 0. So before I put the limits in, I might as well combine that to make it, I think it's good practice to combine your terms before putting in the limits, surely. Do you agree? I hope so. So sine 2 theta pi by 3 to 0. Okay, so I noticed the 0 bit here is not going to produce any values, so I often look at that. Does the 0 actually produce any values in the when you input it, and it doesn't, they're all 0. So anyway, we have a squared bracket 27 pi by 3 minus 20. Now it's useful to know sine pi by 3. We should know this. We really should. Square root of 3 over 2, and also sine 2 pi by 3 is also the square root of 3 over 2. You're basically on the top of your sine graph here. Okay, square root of 3 over 2 there, and this is, if that's back in degrees, 60 or 120 if we're in degrees. Okay, you're going to use a calculator, but really. Anyway, so sine pi by 3, which is equal to square root of 3 over 2 plus the square root of 3 over 2. Minus 27 times 0, I'll put it in. That's 20 0 plus 0. Okay, for what it's worth. Okay, so that gives us a squared times 9 pi minus 19 square root of 3 over 2. Now I shan't bother to do any simplification of that of this stage, because I've noted I'm going to actually work out double this area as well, and add them together, and maybe it'll all simplify itself a little bit. So it's going to be a similar exercise, finding double A2. So that equals to the integral of pi to pi by 3 of 3 plus 2 cos theta squared. Don't forget the a squared d theta. So that equals to, and again, let's not mess around. Square in brackets should be just bread and butter. 9, 3 times 2 is 6, double that's 12 cos theta, and then plus 4 cos squared theta d theta. Okay, right, now again we've already got I've handily written some stuff here that's going to help us with integrating all this. So that equals to 9 theta plus 12 cos theta, so that's 12 sine theta, and we've already integrated 4 cos squared theta. I knew that was coming, so that's sine 2 theta plus 2 theta, and that's from pi to pi by 3. And as before, it's not a big deal here, but I just think it's good practice. Tidy up your terms before we put in the limits. So that's 11 theta plus 12 sine theta plus sine 2 theta between pi and pi by 3. Okay, lovely. So we're going to put in the limits now. Not too far from getting this done now. 11 pi plus 12 sine pi is going to be 0. And sine 2 pi is going to be 0. See how helpful it is not having to shove this in a calculator. Minus 11 pi by 3. And again, 12 sine pi by 3 is equal to square root of 3 over 2. So that's plus 6, the square root of 3, plus, and sine pi by 2 pi by 3 is the square root of 3 over 2. Okay. Okay, so let's just tidy this up then. We've got 11 pi take away 11 pi over 3. So that's going to be 33 pi over 3, take away 11 pi over 3, so that's 22 pi over 3. And then we're going to have, this is naught, this is naught. So this is 6 pi over 3 plus the square root of 3 over 2, so that's 13, the square root of 3 over 2. And don't forget our a squared, I seem to have dropped it. A squared, a squared, a squared, a squared, and then I can just put a squared there. Okay, so we're nearly there now. So the required area as I said, was equal to 2a1 plus 2a2, which is equal to a squared 9 pi minus 19 the square root of 3 over 2 plus a squared 22 pi over 3 minus the square root of 13 squared 3 over 2. Right, that makes it a squared 9, let's put over the common, so that's going to, this is going to be 27 pi over 3 plus the 22, so that's 49 pi over 3. And here we've got 19 minus 13, which is 16 over 2, so that's minus 16 the square root of 3 over 2. Sorry, not over 2, because I've already divided by 2. So that gives us what we want. As required. So that's it. So the main thing to take care of with the limits, and then it's a bit of a slog, but not too bad. Really, anyone who's confident with their integrating trig, sine squared in particular, or cos squared, then should be no problem at all. Okay, so hopefully that helps and takes away some of the mystery of polar coordinates, which after all is something that does particularly bother students, because going from the Cartesian world to the polar world is quite a jump, and it does take a little bit getting used to. Hope you enjoyed it. Bye.